National 4-5 waves, wave properties. In wave properties, we're going to be looking at transverse and longitudinal waves, wave characteristics, wave speed, frequency, period, the wave equation, and a summary of the wave properties. First of all, transverse and longitudinal waves, and here's a short video just to give you an introduction.
Waves transfer energy from one place to another. You should already know how to describe them in terms of frequency, wavelength, and amplitude, which we looked at in another video. In this video, we're going to look at two ways they can be classified. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is travelling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the slinky, but the wave itself moves from left to right, so the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it, it's just the energy that moves along. Transverse waves are usually used to show the wavelength and amplitude. Pause the video and see if you can remember how to label the amplitude and wavelength on the diagram. Did you get them right? The waves on the surface of water are transverse waves. They make the water surface go up and down. All types of electromagnetic waves, like visible light, are also transverse waves. So, now you should be able to describe the differences between transverse waves and longitudinal waves. Remember, it is the energy and not the slinky itself that travels.
Okay, so transverse waves. First of all, let's just remember that all waves carry energy, whether that be sound energy, water energy, particle motion, all waves carry energy. The substances through which the wave travels is known as the medium, so this could be water or air, or in the terms of electromagnetic radiation, a vacuum. In a transverse wave, the particles oscillate, that means vibrate, at right angles to the direction of the wave energy. So you see in the animation, particle motion is up and down, but the energy transport is along left to right. Water and light waves are both examples of transverse waves, and traditionally when we think about waves, we think of water waves and we see them going up and going down with the tide. Longitudinal waves are a little bit different. In a longitudinal wave, the particles oscillate backwards and forward in the same direction as the motion and energy of the wave. So we see in the animation, the particle motion backwards and forwards, the energy is moving along the direction of the particle motion. Sound is an example of a longitudinal wave. So when you produce a sound, the particles of air in front of you start to vibrate, and then they vibrate and pass that energy onto the particles in front of them, and so on and so forth, which is why you can't hear people that are very far away, because every time the energy is passed from one particle to another, a little bit is lost, So faraway objects receive only a very small amount of the energy of the original sound wave. When we're examining wave characteristics, we look for certain features: the wave crest, or sometimes known as the peak, the trough, amplitude, wavelength, wave speed, period, and frequency. And what we're looking to do is to be able to define each of these features. So let's look at a wave. Wave travels up, wave travels down. This is an example of a transverse wave. We can see the point where we have the highest part of the wave is called the crest. The point where we have the lowest part of the wave is called the trough. And if we look from the start of the wave to where the wave starts to repeat itself, we can see regular crests, regular troughs. The amplitude of the wave is measured between the central line and a crest, but also could be measured between the central line and the trough. Again, looking at those similar points, the similar points between here where the wave is starting to increase and then where the wave starting to increase again, or here between the trough and the trough, or here between the crest and the crest, the points in between where the wave starts to repeat itself is known as the wavelength, the length of the wave. So let's look at those key definitions. The crest is the highest point of the wave. The trough is the lowest point of the wave. The amplitude is the height of the wave. And the wavelength is the length of the wave. Going back to our wave, some waves move relatively slowly, going from one position to another position. I'll move a little bit more quickly. And other waves still, electromagnetic radiation, will move even quicker still. This is known as the wave speed, the speed at which a wave travels, the time taken to go from one position to another position. Our wave travels from one point to another point. The point at which it has completed one cycle, the time for one complete cycle, is known as the wave period. Once the wave repeats itself, we call that 2t, 2 times the wave period. So we can use the wave period to predict how long it's going to take for a wave to travel. Different waves have different characteristics. In this example, I see 2 complete waves on the screen. The period is exactly in between those 2 complete waves. The time for one complete wave is quite long. In another wave, keeping that point t on the axis, we see this wave has almost twice as many waves in the same period of time. This wave, I've got far more waves occurring within the same period of time. Frequency is a measure of how many waves pass a point per second. So let's kind of summarize that a little bit. Wave speed is how fast a wave travels. The period is the time for one complete wave. And the frequency is the number of waves passing a point per second. Summary. A wave crest is the highest point on a wave. A wave trough is the lowest point on the wave. Amplitude, A, is the height of a wave. Wavelength, lambda, is the length of a wave measured in meters. Wave speed, V, is how fast a wave travels, measured in meters per second. Period, T, the time for one complete wave, measured in seconds. And frequency, F, the number of waves passing a point per second, and that's measured in hertz. One thing to note here is that there's no specific unit for amplitude. Amplitude in the case of a water wave could be measured in meters, but if we were looking at the amplitude of an electrical wave, we could be looking at measuring that in current, amperes, or voltage, volts.